What's going on, guys? It's Grayson here. So, for those of you that don't know, I am currently, and by currently, I mean in the future for me talking right now, I will be out of town. That was probably the most confusing way that I could have possibly worded that. I'm going to be going out of town. I'm recording this before I leave so that I can upload it while I'm gone. Hopefully, everybody knows what I'm talking about. Anyways, I have mentioned before previously, both on some community posts and around, that I have given a presentation at my local university to the graduate cosmology class about entanglement and quantum entanglement and cosmology. And a lot of you expressed an interest in that lecture. So I didn't actually record the presentation to the class, but I still have the PowerPoint for that. I had a little bit of technical difficulties getting the PowerPoint in Keynote to play nice with StreamYard and getting it to share the screen. So, in short, the actual format of the PowerPoint is kind of messed up. Some of the images were lost, all the animations were lost, but that's fine. All the information content is still pretty much there, and so it's still a really fascinating talk, and I think it's going to be really interesting for you guys that are at all interested in like quantum physics or the universe at large scales or just having your mind blown in general. This is going to be really interesting. So the way that it's structured is I first talk about sort of the history of quantum entanglement, what it is, and how it was developed up to the present. And then we get into what's going on with entanglement in actual cosmology itself. How has quantum entanglement been used in cosmology, which is the study of the universe at the very largest, grandest scales of space and time? And how quantum entanglement informs us in cosmology and can be a tool for helping us understand the universe at these very large scales, which is very counterintuitive considering quantum entanglement is a quantum process. So it's really fascinating. I can't wait to get into it. So let's just go ahead and begin here with the PowerPoint. I'm going to go ahead and minimize myself so everybody can read what's on screen. This is not the first slide, but this is just an overview of what quantum entanglement is. I actually started with a quote from one of the founders, one of the leading luminaries of quantum mechanics, Erwin Schrödinger, who said that he would not call that, meaning quantum entanglement, he would not call that one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. So that's what Erwin Schrödinger was saying about quantum entanglement. He's saying that this is the key principal thing that makes quantum mechanics so weird. So it's a pretty important thing to understand. And there's a ton of misinformation about quantum entanglement and spooky action at a distance and quantum teleportation and all of this stuff. And just reading, what people say about it or reading what the science journalists and pop sci articles are saying about it. It's just, there's just so much misinformation out there. So I just wanted to go over what it is, right? Entanglement is a non-local quantum correlation that can stretch over any distance. So in the class, I kind of had this as an interactive part of the presentation, where I showed that there's only one word in this definition that is even weird or strange or non-intuitive. If the word quantum was not there, then I don't think anybody would have any reason to think that there's anything spooky going on here. If I just said it's a non-local correlation that can stretch over any distance, well, this is what I did with the class, right? I had two little boxes and I put a green piece of paper in one and a red piece of paper in the other. And I sort of didn't show them which piece of paper was in which box. And then I gave one student one box and one student the other, and they didn't see which one they had. And I asked one student to open hers, and she had the red piece of paper in hers. And so then everybody knew that the other girl had a green piece of paper in her box that she had. So no matter where she went on the planet, even if we sent her to Pluto, beyond any ability for like light to be able to instantaneously travel from one point to the other, as soon as one person opens their box and sees that they have the red paper, they instantaneously know, no matter where in the universe the other box is, that the other girl has a green piece of paper. So there's nothing weird about this example. This is an example of a non-local correlation that can stretch over any distance. It's just a correlation, right? The weirdness is what's when we introduce a quantum correlation. So we have to unpack what is meant when we introduce that this is not just a classical correlation, which can stretch over any distance, just like the example shown, but it's a quantum correlation. So to kind of unpack what is meant by a quantum correlation, I think it's important here to introduce this phrase "spooky action at a distance," right? Because this is sort of this can be traced back to Einstein, this quote, and it's often attributed to Einstein saying quantum entanglement is the spooky action at a distance. But I will actually be arguing that that is not the case. So, Einstein was kind of the first one to really put quantum entanglement on the map in terms of getting a lot of buzz and people to talk about it. Like some of the early founding members of like the field of quantum mechanics, they knew about these kind of ideas of quantum entanglement, but they didn't have a name to describe it as such. They there was talks about this like at the Solvay conference in the late 1920s, and Schrodinger and Einstein had talked about this before, but it was really with the publication of the famous EPR paper, the Einstein-Podolsky-Rosen paper in 1935, which really is what is seen as the seminal paper that really established quantum entanglement. It's the EPR paper, and when you read it, um, it's a very philosophical paper. It's very short. It's worth a read. It's really interesting. But you can see how this paper, right? It was titled "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" So the EPR paper is actually arguing that because of this phenomenon of quantum entanglement, which again the term still had not been coined yet, they were arguing that because of this phenomenon, where you have these two particles and you've got this sort of entangled phenomenon between them, this non-local quantum correlation, they're arguing that this implies that quantum mechanics itself cannot be considered complete. And it was, you can see here, the New York Times. I mean, can you imagine back in the day where people were so into like popular scientists that it was right here on the New York Times on Saturday. It says Einstein attacks quantum theory. Like this was front page news in 1935. It's kind of, it's awesome to see that like such a, a publication in the Physical Review would be making front pages like this, but it's awesome. And I have this quote right here next to it, which is actually not from the EPR paper, but this is the quote from Einstein where you first see the mention of spooky action at a distance. And this was actually to a letter. So after Einstein published the EPR paper, then he started a correspondence with Schrodinger, and Einstein and Schrodinger wrote back and forth to each other in the years after the publication of the EPR paper. And that is where, from those letters, that's where we get this spooky action at a distance phrase. So I think it's actually important to read the context for what Einstein is talking about when he brings up this spooky action. So he's essentially making this argument that quantum mechanics is incomplete. So he says, I cannot seriously believe in quantum mechanics because the theory cannot be reconciled with the idea that physics should represent a reality in space and time free from spooky actions at a distance. I am, however, he continues on, not yet firmly convinced that it can really be achieved with a continuous field theory, although I have discovered a possible way of doing this, which so far seems quite reasonable. And just for clarification, Einstein would continue to pursue this idea unsuccessfully for the remainder of his career. So he goes on. The calculation difficulties are so great that I will be biting the dust long before I myself can be fully convinced of it. So yes, Einstein knew that this was going to remain out of his grasp. He says, but I am quite convinced that someone will eventually come up with a theory whose objects connected by laws are not probabilities, but considered facts, as used to be taken for granted until quite recently. So you can see here that Einstein's saying, Einstein himself, may not be able to introduce this theory that gets rid of these quantum probabilities. But he believes that someday someone will do it. And again, this was almost 100 years ago now that he's written it. So we will touch on later on whether or not I think you know someone will one day come along to vindicate what Einstein is saying here, or whether Einstein was wrong. You're going to have to tune in to the end of the presentation to get my ruling on that one. Um, but this is the first instance where he actually says spooky action at a distance. And I make the argument, if you read the EPR paper, that it's pretty clear that he's not talking about just quantum entanglement, because when he describes this as action, right, there's not really an action that's going on with quantum entanglement. There's the collapse of the wave function, which is what we're going to get into. But basically, in the EPR paper, they show, that this spooky action at a distance thing can happen with just one particle's wave function. You don't need to have two particles entangled to be getting this very strange, spooky action at a distance, which is what Einstein, I am positing, is referring to wave function collapse as the spooky action, not quantum entanglement, but actually just wave function collapse in general, which of course, quantum mechanics has a probabilistic nature. Nowhere is that more evidence than with wave function collapse. However, many physicists, myself included, would make the argument that wave function collapse is not an actual physical action that is happening. It is merely an update in our information, an update in our understanding or knowledge of the system. It's an instantaneous update in knowledge. It's not in itself a physical action. So this is the argument about what Einstein meant by spooky action at a distance. But let's go on to get a little bit more of a formalized basis, a knowledge of what quantum mechanics, what quantum entanglement is actually describing. So, in one of the letters that I mentioned, in response to the EPR paper, Schrödinger is the one who coined the term Verschrankung, which, again, I apologize to all my German viewers for that horrible pronunciation, but Schrödinger himself translated this German word as entanglement. So Schrödinger was the one that coined it. And then years later, again, that he coined in 1935, years later in 1957, Aharonov and Bohm introduced a very quintessential example of the formalism that is basically used in most textbooks today when just describing the general mathematical way to just generalize the concept of quantum entanglement. And you can see it right here. And if that doesn't mean anything to you guys, this is sort of a way to describe what's happening in English. So as you can see here on the left-hand side of this equation, we have one wave function, this psi of 1 and 2. So that's one wave function that's describing two or potentially more particles. We could do psi of 1, 2, and 3 and describe these three particles here. But this is one wave function that describes two particles. And you can see here that basically when this is described, when one particle is measured to be in a certain state, that is altering the wave function for the other particle. So a measurement on one particle changes the wave function of the others because they both are sharing the same wave function, which is like a statistical, mathematical statistical description of the system. You can describe it as a wave function. So that's what quantum entanglement is. It's when two or more particles can be described mathematically in the language of quantum mechanics using one wave function. And any change to one particle is thus going to change the wave functions describing all the particles in your entangled system. So I just want to clarify, now that we've sort of described what is meant by quantum entanglement in the formalism of quantum mechanics, I need to briefly mention and clarify a misunderstanding I see all the time. And that's this idea that, oh, well, if we have, these two particles and they're entangled and one's on Mars and one's on Earth, and I affect one here on Earth, then over on Mars, they'll be able to instantaneously detect whatever I did to it on Earth, and you can sort of send this information. You can mess with it on one side on Earth, and over on Mars, they'll instantaneously be able to get the information update that you messed with it. But this is not the case. There's such a thing called the no signaling theorem, and that is that information cannot travel faster than light. And it has been physically and mathematically shown that quantum entanglement does not violate the no signaling theorem. So basically, if you were to perform a measurement or interact with your entangled particle here on Earth, and then you have a partner on Mars who has the other entangled particle, if you were to mess with it here on Earth, you might be able to now understand exactly what state that your partner's particle has on Mars. You might know that. You have that knowledge update because you've performed the measurement locally on your particle. But over on Mars, they have no idea until they measure their own particle what state it's in. You could call them on the phone, but that's going to be going at the speed of light, right? It's going to be, it's going to be going less than the speed of light. Basically, the information traveling between you and Mars on the phone, any other conventional means, going to be less than the speed of light. So the no signaling theorem is preserved. Quantum entanglement does not violate faster than light information travel. So that was important to clarify. So, the next step in our historical timeline of quantum entanglement is another huge luminary, an absolute genius in the field, John Stuart Bell, who published a response to that EPR paper in 1964, so several decades later. And it took the analysis much, much farther than Aharonov or Bohm or anyone before him. Bell deduced that if separate measurements are performed on each of the entangled particles, then any local hidden variables imply a mathematical constraint known as Bell's inequality. Remember, Einstein was saying that there are some sort of local hidden variables that are not probable. They're not just probabilities. Okay, they're facts. They're concrete facts of the world. There's some kind of hidden variables that we don't know about that are explaining everything that happens in quantum mechanics without any probabilities. Everything is deterministic, basically. Bell is saying if that is the case, then that introduces a mathematical constraint on your system, Bell's inequality, which can be measured. That's the key, is that you can actually measure this. So Bell showed that quantum mechanics predicts correlations that violate this inequality. Now you have two competing models. You have the model of local hidden variables, like Einstein wanted there to be some non-probabilistic hidden variables. And then you have the model of quantum mechanics, which has these probabilistic quantum correlations that violate Bell's inequality. It's finally testable thanks to Bell's ingenious idea here. So we needed the actual experiments. And it was not until 2022, just 2 years ago from when I'm recording this, that the Nobel Prize was given out for the experimental verification of Bell's inequalities. The exact quote from the Nobel Committee was that the prize was given for experiments with entangled photons establishing the violation of Bell's inequality and pioneering quantum information science. So as you could tell right there, Bell's inequalities were violated, meaning that the prediction of quantum mechanics, the probabilistic nature of quantum mechanics, not the local hidden variable theories, the quantum mechanics prediction was successful. The Nobel Prize was given out for verifying the violation of Bell's inequality, thus for verifying the existence of these quantum correlations that seem probabilistic that Einstein did not like so much and wanted to try to find a theory that got rid of. It turns out the experimental verification is on the side of Einstein's quantum opponents. So, where do we go from here? There are I want to make the point before we move on that these are not the only experimental verifications of this. These are just the ones that were awarded the Nobel Prize: Elaine Aspect, John F. Clauser, and Anton Zeilinger. And I also I did want to point out also that Clauser is a prime example of Nobel syndrome, where a scientist will win a Nobel Prize and then start making like radical, outlandish, crazy crackpot claims about fields of science outside of their own. Like Clauser has some like absolutely like insane person ideas about some very different fields of science outside of his specialty in physics. So yeah, he's a prime example of that. I mean, I'm not even going to get into all of his beliefs here, but they're pretty whacked. But there's been other experiments that have verified this violation of Bell's inequality that have not won the Nobel Prize. For example, the Large Hadron Collider, the LHC, in 2023, they had their observation of quantum entanglement in top quark pairs using the ATLAS detector. So they detected a violation of Bell's inequality using their particle accelerator over at the LHC. So this is pretty well established that Bell's inequality in reality is violated. And I saw lots of like popular science news sites trying to say that these scientists won their Nobel Prize for proving that reality is not real. It's like, okay, okay, like the amount of hype and the amount of crazy claims about these Nobel Prize winners was just insane when it happened. So we gotta clarify what exactly a violation of Bell's inequality means, because there's a couple different options for what meaning we should take from these results. Here's three possible conclusions, right? And you'll notice that the popular press really did not cover any of these at all. They just said, oh, reality is not real. That's what the scientists are saying. Okay, here's the three conclusions we can draw here. Three possible possibilities. One, quantum mechanics is correct. There are no local hidden variables. Quantum mechanics is a complete theory, unlike what Einstein wanted, and quantum mechanics is non-locally causal. It's a non-locally causal theory. There's no local hidden variables, and quantum mechanics is all there is. That's one possible conclusion: is that Einstein is wrong, quantum mechanics was right, and that would be supported by the experimental evidence that we have now. But it's not the only conclusion that we could reasonably draw from these experimental results. There's a second one and a third one. Number two is that there are hidden variables, they're just non local. Thus, you could say reality is not locally real. There's some sort of hidden variables, like there are variables that are determining the outcomes of measurements that are non local, as in they're not, for a local interaction, like between this finger, I have to locally interact with it. I can't do anything over here that's going to interact with this finger non-locally. But, you know, a possible interpretation of these results with Bell's inequality is that there are non-local hidden variables. This is a popular interpretation of these results as well. It kind of goes into a lot of different ideas in string theory and other kinds of cutting edge theoretical science. Now, possibility number three, which I'm seeing I incorrectly labeled with a Roman numeral of 2. Great job, past Grayson. The third possibility is that there are local hidden variables, but if there are, then measurement independence must be violated. So measurement independence is a key assumption of Bell's math that he uses to construct the Bell inequality, basically. So measurement independence is assumed. If we do not assume measurement independence and instead allow measurement independence to be violated, which is kind of known as superdeterminism, then we can have local hidden variables. So to tell you kind of what that means, the measurement independence is basically the idea that your choices of how you measure a system is independent. Like what you choose to measure, the choices you make about your measurement, what kind of device, what you're going to measure, all these choices of measurement are independent of the local hidden variables that you would be trying to measure. They'd be independent of what you're trying to measure. Measurement independence, for that to be violated, there would have to be some kind of dependence between these hidden variables and your choices of how you measure them. And so it's kind of known as superdeterminism, because there would be some sort of past past information or past state of the universe that would be determining both the hidden variables and what you're choosing to measure them with. So that's the third possibility, superdeterminism. I'd say it's probably the least popular of the three interpretations, but all three are possible based on the evidence that we currently have today. So finally, we can get to, now that we've summarized quantum entanglement from its inception to all the way to where we're at today with the 2022 Nobel Prize and beyond. Now we can talk about, finally, what relevance does any of this have for cosmology, right? Because I gave this lecture for a cosmology course, and there's a few things that we need to keep in mind to really answer this question, right? Because on larger scales, quantum effects become negligible. It's very counterintuitive that quantum effects like entanglement would have any appreciable impact on these very large cosmological scales. Interactions between surrounding particles cause them to become entangled, delocalizing the phase coherence to the whole system. So this is called quantum decoherence. This is sort of explaining why it is that on larger scales quantum effects become negligible. It's because every interaction between these quantum particles causes this entanglement between them, and it delocalizes the quantum behavior of the entire system over more and more and more particles. And so this sort of quantum-y nature of the entire system is being decohered. The more particles you have, the larger the scales become. For entanglement to be relevant for cosmology, then we have to look to the extremes, to like the black holes and the early universe, where the conditions are just so extreme that you're pushing these quantum effects to becoming relevant again. Let's look at black holes, right? There is a certain paradox known as the black hole information paradox, where in quantum mechanics, information cannot be lost or destroyed. But in general relativity, black holes were predicted to destroy information as they evaporate. Hawking showed that black holes evaporate, and then suddenly all the information of all the stuff that it swallowed would just be gone. So that was a major unsolved paradox between quantum mechanics and general relativity, just not playing nice with each other, until the paradox was resolved using entanglement. Now, the paper I cited here is Almhiri et al. 2019. I'm sorry if I butchered that pronunciation, by the way, but there are actually several series of papers in the 2010s that are sort of laying the groundwork for this. I just think Almhiri et al. Really laid it out very well in 2019. But essentially, information is conserved because it becomes entangled with the escaping Hawking radiation. As these black holes evaporate, they emit a bunch of Hawking radiation, and the actual information that is swallowed up by this black hole becomes entangled with this Hawking radiation that's emitted, so that actually the information is conserved and not lost or destroyed. And it's only because of quantum entanglement that this paradox was able to be resolved for like black holes, some of the biggest, most cosmologically relevant objects in the universe. We can look to another very recent and major innovation in the field, and that's ER equals EPR. So this was a conjecture. It is a conjecture, a hypothetical conjecture, proposed by Susskind and Maldacena in 2013. And for those of you that know me, Lenny Susskind is like one of my favorite physicists that's currently alive. I love Susskind. I've watched his lectures. He's amazing. And he teamed up with Juan Maldacena in 2013, who has one of the most cited papers in all of theoretical physics, his like 1997 paper on ADS CFT correspondence, which I do have a video on in the based theory playlist. But these two like titans came together and came up with ER equals EPR. So you remember, right, that earlier we talked about the EPR paper as being the paper that established quantum entanglement historically. So that's the same EPR. However, there's another Einstein, Podolsky, Rosen, remember, was EPR. That's quantum entanglement, a shorthand for quantum entanglement. Einstein and Rosen, two of those three in the EPR paper, actually went and published another paper where they established wormholes called Einstein-Rosen bridges in general relativity. So this concept of Einstein-Rosen bridges from general relativity, actually Susskind and Maldacena showed that in certain mathematical formalisms, like in like it's mainly they initially showed it in string theory, that they were mathematically equivalent. ER was equivalent to EPR, meaning that wormholes were equivalent to entanglement mathematically, at least in the way that Susskind and Maldacena were demonstrating with their formalism, which really opened the which really opened Pandora's box in a lot of ways for thinking, and showing that, look, one of the biggest unsolved issues in physics is resolving quantum mechanics and general relativity, because they don't seem to play nice to each other with each other. But here we have not just one example, right? We already showed here how quantum entanglement was resolving this paradox between quantum mechanics and general relativity. But here we have another example of of we have general relativity and quantum mechanics describing two seemingly separate phenomenon, but you can see here that actually there might be a mathematical equivalence between them. And lots of work has been done on ER equals EPR in theoretical physics since 2013. It looks really, really promising. So I also wanted to touch on entanglement in inflation, and this slide is kind of messed up, but at least it's readable. So basically, large scale cosmological structures are generated from quantum fluctuations expanded by rapid inflation. So here we can see sort of a natural intersection between the very small and the very large, is that the very small is being blown up by inflation to become very large. Maybe to have this quote from these two researchers here, that the expansion of space-time generates entangled particles whose correlations can theoretically be measured to deduce the values of cosmological parameters. So essentially, these two researchers in 2012 proposed that there should be certain relationships that are maintained, certain correlations that should be observable if inflation really blew up all these entangled pairs. There would be correlations that would be preserved from that could, at least in theory, be observed and used as a cosmological probe, like we have other probes in cosmology to measure some of the fundamental constants of the universe. And then we can have just one more independent means of measuring these values and cross corroborating with other methods. And then one more quote from a paper actually from 2024 that was going back and revisiting this concept from the 2012 paper. And because in the 2012 paper, while it was theoretically possible to measure such things, it would require several orders of magnitude more precise equipment than we currently have. So engineering wise, technologically, it was not feasible in 2012 or currently in today with the methods introduced by that 2012 paper. But in 2024, we have here the essentially the quote is, rapid expansion generates cosmological entanglement entropy carried by long distance modes that go through the process of horizon exit during inflation and are accessible to experiments today. So Butavis et al. Just this year in 2024 proposed that there's this entanglement entropy, which actually could be measured using instruments of the sensitivity that we have today. So this was just very recent in 2024. So this is going to be something to watch to see whether or not the entanglement entropy of the universe could be measured on cosmological scales in the near future. It's a pretty exciting field of scientific discovery here. So the last thing that I really wanted to touch on, or I guess second to last, but is this idea of emergent space-time. Another way that we have quantum entanglement playing a defining role in cosmology, right? And so here are several very high-profile physicists. These are titans in the current field. And here's what they're saying, right? These are direct quotes. Here's a quote from Nathan Seiberg from Princeton, a physicist from Princeton. He says, "I am almost certain that space and time are illusions. These are primitive notions that will be replaced by something more sophisticated." Andrew Strominger of Harvard said that the notion of space-time is clearly something we're going to have to give up. Of course, famously, Nima Arkani Hamed, also of Princeton, said that the very notion of space-time is not a fundamental one. Space-time is doomed. There is no such thing as space-time fundamentally in the actual underlying description of the laws of physics. And finally, Lee Smolin, another favorite physicist of mine, said there is fundamentally no space or space-time. So, what are these physicists talking about? What is causing them to say that space and time are not real? I mean, space time is certainly something that most people take for granted. They don't even think about. I've had numerous arguments with people that are claiming that space and time are not even real, that they're just constructions of humans, and they're just illusions. But these physicists are saying that actually they are illusions, and that they're emergent from more fundamentally underlying physics, and that there's no such thing as space and time. So how do we mesh this all together and make this make sense? What are they talking about? So there are several papers that are mentioning this, right? There are reasons to independent reasons to be skeptical about whether or not space and time are fundamental, like namely the fact that the way that you look at smaller and smaller things is by using more and more and more energy. That's essentially what particle accelerators are doing, or that particle accelerators are essentially functioning as incredibly powerful microscopes, allowing us to view the smallest things in the universe, and it requires a tremendous amount of energy. Eventually, you reach a hard limit where you cannot look any smaller. There is nothing smaller that has any bearing, because when you try to look, the amount of energy in such a small amount of space just creates a black hole. Like, there is a reason for a limit, that there is not just an infinite amount of space that you can keep cutting in half, and it's just continuously infinite down to whatever sort of small scale you want. There is a hard limit where these things have a certain amount of quantum properties that we really need a theory of quantum gravity or some other theory to describe to us what is going on at the very smallest levels of space and time. But the very notion of space and time at these smaller levels doesn't seem to make sense. So several physicists have actually used entanglement to explain this relationship. Van Ramsdonk of at this time, he was at the University of British Columbia. I think he's still there today. He said space-time is just a geometrical picture of how stuff in the quantum system is entangled. And you can see that his paper here is literally called Building Up Space-Time with Quantum Entanglement. Remember that idea that quantum entanglement is the equivalent of an Einstein-Rosen bridge, a wormhole. This is where it becomes relevant, because if you have all of these particles, and there's fundamentally, on a fundamental ontological level, there's no space between them, right? But they're connected to each other through these non-local quantum correlations, this entanglement. And it's actually the buildup of when you have the entire system where every single interaction creates another entangled connection between that. You're connecting all the entangled systems into all the other entangled systems every single time they're connecting. I'm not sure if this is making a lot of sense right now with the way that I'm describing it, but if you're thinking about every single interaction between every single particle creates a new entangled connection, and that each and every particle is already in countless amounts of entangled connection with every single particle that it's already interacted with in the past, then you have this massively complex network of entanglement. And actually, the way that this correlates things together it sort of creates, as you get at larger and larger scales, it emerges this system of space where you all of a sudden it gives the appearance as if there's a distance between events, when in reality there's simply a degree of how entangled their particles are. So if you guys are curious about like what this entails mathematically, I really would recommend Lee Smolin's work, because he's shown like how you get space actually emerging from this network of entanglement, and he's shown how the degree of entanglement directly um, leads to the emergence of distance in space. It's like really, really amazing work. Again, that's Lee Smolin, and it's part of his energetic causal set theory. That's what you would search for to find this. I don't know why I didn't include that in these papers here, but these are multiple different people here. I mean, you can see that one of these papers is from Sean Carroll. I think it's from 2016, Recovering Geometry from Bulk Entanglement, Space from Hilbert Space. So again, this is a paper that Sean Carroll co-authored, showing where you can recover the geometry of space and space-time from just having quantum entanglement. And the same thing was shown by Brian Swingle, who was then at MIT and I think is now at Stanford. In his paper, Entanglement, Renormalization, and Holography, you can see the quote here that you can think of space as being built from entanglement in this very precise way using tensors. The tensor networks that Brian Swingle used were developed for actually condensed matter physicists as a method to track quantum states of huge numbers of particles. So like literally just the science from such disparate fields of quantum mechanics, general relativity, and condensed matter physics is coming together to seem to indicate to us that space-time emerges from quantum entanglement. At least that's what some of this evidence and some of these physicists are seeming to suggest. It's certainly not concretely demonstrated yet, but it certainly is just one of the most mind-blowing things that I know that I could possibly think about. The last thing that I wanted to include here, just as a little bookend at the very end of the presentation, because I don't know much how you can get more mind-blowing than literally space itself being emergent from quantum entanglement. But I wanted to highlight this because this was an extremely new just a new paper from 2024 from the IceCube collaboration, which is just one of the coolest scientific instruments on the entire planet and really underrated. Here we have a picture of the IceCube lab. This is actually in Antarctica. And here's the Eiffel Tower, guys, for scale. I don't know if you can even see that. If the screen is even big enough for you to see that tiny little Eiffel Tower there in the bottom, but this thing is massive. This is huge. This is a giant chamber that's literally dug into the ice, and these strings hang from it. 86 strings, 60 sensors on each string, and these sensors are for detecting neutrinos. And neutrinos are, basically like dark matter. Like they barely they don't really interact electromagnetically at all. They only really interact like with like gravity, and like dark matter does, and then they interact very weakly. And so this massive detector is necessary to detect just these neutrinos very weakly, even though trillions of them are passing through your body like every single second. They're so rare to interact with anything, and they interact so weakly. It literally takes a detector of this size to detect any appreciable amount of them. But in 2024, just in March of this year, they did an experiment using entanglement to measure quantum gravity, which has got to be like just one of the coolest things. I mean, you guys know quantum gravity is one of the mysteries of the universe that I am most interested in. And just I had to include them at IceCube using quantum entanglement to measure quantum gravity and test predictions. So this is what they did, right? The name of the paper was A Search for Decoherence. Remember, we talked about decoherence earlier, from quantum gravity with atmospheric neutrinos. Here's the relevant quote, right? If the metric of space-time has a quantum mechanical description, right? Quantum gravity. Gravity is the curvature of space-time. So quantum space-time would be quantum gravity. Its fluctuation at the Planck scale, the very, very smallest scale, are expected to introduce non-unitary effects that are inconsistent with the standard unitary time evolution of quantum mechanics. Basically, a predictable, a testable, falsifiable prediction of quantum gravity as that would differentiate it from the quantum mechanical description. Neutrinos interacting with these fluctuations, these quantum gravitational fluctuations, would lose their quantum coherence, and we would be able to detect this loss in quantum coherence in the entanglement characteristics of the neutrinos that we detect at IceCube. I mean, ingenious setup. I mean, I never would have thought of this. This was amazing. Whoever thought of this, give that person a raise. But here's the thing, though. They did not detect any result. They just detected what quantum mechanics predicted, the unitary time evolution of that is predicted using the Schrodinger equation. They did not predict, or they did not detect rather, any non-unitary effects from any kind of quantum gravitational fluctuations. Look at that, guys. The plot continues to thicken. I mean, could this problem possibly even get any more interesting? I mean, I am on the edge of my seat here with all of the quantum gravity research, both theoretically and experimentally, and it's so cool that in 2024, in today's day and age, there are actually experiments being done to measure quantum gravity, or at least test predictions about quantum gravity in experiments like this. Like, this is the most insane scientific instrument. This is right up here with like the LHC, like the largest particle accelerator. Like, this is amazing. How could humans do this? I mean, people think that like the pyramids are really impressive, and like they are. They're one of the coolest wonders of the ancient world. But like this right here, this would be in my short list for the wonders of the modern world. Like, this to me, Ice Cube is so much more impressive than the pyramids. I mean, even factoring in the time period, like it's mind blowing to me that nowadays, with today's technology, that we could do something like Ice Cube. Um, but yes, anyways, guys, that was essentially the presentation I went into a lot more details here with you guys because I was time limited when I gave this talk in person. But hopefully this was a deepening understanding that you could maybe learn a couple things about either the physics or the history of quantum mechanics and quantum entanglement in particular, and that you were able to then well, I not necessarily that you were able to piece together how that fits into cosmology, but just thinking about how these very, very small phenomenon like quantum entanglements can actually be relevant to fields like cosmology at the universe at the very largest scales. It is one of the coolest things I'm aware of. And in cosmology, they're not really teaching about the relevance of quantum mechanical effects or quantum entanglement. Sometimes when you get like into the niches, like with inflation, then it becomes relevant. But just in general courses, I mean, you're not learning about quantum entanglement at all. Like, some of the grad students were coming up to me and being like, "Wow, like I really didn't know how quantum entanglement was playing roles in the kinds of things that like we're working on." I mean, it was really cool to see, but also like, I mean, you have to take quantum mechanics to pursue a degree in cosmology. So they knew the basics of the science very, very, very well. I mean, they understand the math of quantum mechanics, they understand quantum formalism, but actually showing how that's relevant in their own field in a way that like they hadn't thought of. That was so cool to get to convey that information and to get to like share in that epiphany. Um, and to get their own thoughts about um, you know the how cosmology can use this information and where they can go from here, and how the fields of the very small and the quantum physicists can work with the very, very large, the cosmologists, and they can collaborate and actually make progress in both fields. It is just one of the coolest things ever. And I gotta say, like, the stuff that keeps me up at night, the stuff that I love thinking about, is some of the stuff that I covered in this presentation. Like, Susskind and Maldaceni's work about ER equals EPR is one of the most mind blowing things of all time. Like, I briefly lost a little bit of interest in physics in college, and then when I learned about ER equals EPR, that like literally just reignited all the love for physics that I had in high school. Um, it was like literally research in this field that reignited one of my passions for like my passions for one of my favorite areas of science. So like this stuff is very, very near and dear to me. I literally think this stuff is like the coolest thing ever. And Yeah, I mean, just the idea, like, I would say that this might be my Roman Empire, guys. Like, I honestly spend probably at least once a month. I think about what it would mean for space and time to be emergent from more underlying physics based on quantum entanglement. Like, this is what I'm thinking about. This is my Roman Empire, guys. That my obsession, my like little my shower thought that I enjoy thinking about what kind of implications that this could have for my understanding of reality. Um, so yeah, I will be definitely watching this field very, very closely. As you could see, I mean, I think I used two papers from 2024, one from 2023, and the Nobel Prize from 2022. I mean, this is a very, very recent and like current topic in physics where new things are coming out all the time. So, if any of you see anything out there that you think, wow, Grayson would really love this, like I would love it, please do think of me. Please do send those papers my way. I would love to see them because you guys know I love this topic, and I would if there's any like update on any of this topic, I will probably be covering it on this channel because like this is super cool and I want to share with you guys about this topic in particular: quantum entanglement, the emergence of space-time, quantum gravity. I love this stuff. This is my bag. Hopefully, you guys are on the same page as me and you guys are also nerding out about this stuff and loving learning about this together with me on this channel. So, if you want to stick around, you guys already know, hit that subscribe button, hit that bell, like the video, do all the things. Stick around because I will be back from my road trip and be back with more debates, more debunkings, more live streams. We're all going to be back on on a normal non-summer schedule soon. So bear with me on that. And yeah, just look forward to more on the channel for the rest of the year. And with that, guys, I'm going back on the road. And I hope you guys stick around and stay curious and keep learning and subscribe for more. Have a great rest of your day.